The theory behind quality printing is fairly simple. The right amount of plastic, to the right location, at the right time. This sounds easy. So tell me, why is it that we struggle so much with our high-end machines to achieve the same print surface quality as a Prusa or a well-tuned Ender 3? Every picture or video showcasing printed parts on the internet will make use of a soft light coming from the side to make your part look good. Very rarely do we see these prints under a sharp light coming from the top. In this video, I will be using the worst lighting conditions for FDM printing ever. Be ready to see some very ugly layer stacking. I think it is one of the biggest untold truths about a lot of high-end printers. Until now, luck has been playing a huge role into your printer's ability to produce nice wall surface quality. I may receive rocks for making this comment, but I can tell you that this was the case for my printer as well, until now. Today we will find the answers to your surface quality issues once for good. What could be the cause of this artifact? Sometimes horizontal or at angle, other times creating irregular surfaces. Let's try to isolate which of these three elements could be responsible. The timing portion of the print is managed via the software. Extruder motor needs to be in perfect sync with X and Y movements. The pressure advance function will ensure that the right amount of plastic is available for starts, stops, and during cornering. Since I used vase mode for this cylinder, pressure advance would not have much impact because there is no stop and go. It is a continuous and steady extrusion flow. Therefore, I don't think timing is involved in what we're looking for today. The next probable cause is the positioning of the nozzle. On the Havort, I took extra care about the location, alignment, and stability of the X and Y gantry during design. I selected quality parts and validated the installation at every step. The typical artifact from a defective X or Y axis would repeat itself at the same spot for each layer. This would eventually create a vertical pattern that we don't see right here. An horizontal artifact could be related to Z-wobble. On a Core XY, Z-wobbling is usually caused by the lateral movement of the print bed due to misaligned or crooked lead screws. You can see my previous video on the topic right here. The triple Z mounted on bolt screws for this printer is the part that gave me the most challenges. But I have reached my goal with the Wobble X isolators. Thanks to my good friend Oleg for coming up with this idea. You will see more on this solution in a future video, so make sure to subscribe and activate the notification button so you don't miss any of that. The issue I'm looking at right now has a weird behavior. The pattern distance will vary if I change the size of the part being printed. Therefore, chances that it is the result of Z-wobbling are very slim. Z-wobbling would be constant no matter what I print. The same distance between each artifact would repeat across the print. So if it is not X or Y, if it is not Z, and if it is not the timing, this leaves us with the amount of plastic being extruded. Really? But you're going to tell me my extruder was perfectly calibrated using the 120 and 100 mm technique, and then with the single wall cube to calibrate the flow multiplying factor? I've even performed PID tuning of the hot end heater with cooling fan on and filament extruding. How can this be related to extruding system? I never thought of deep diving into extruders until I made a Bowden adapter for my printer. Magic! The nicest print I ever produced appeared in front of my eyes at the first use of this Bowden setup. Why is Bowden producing such nice prints? Could it be that our very short path direct drives extruders are in fact too much direct? Could the dampening effect of the Bowden tube and the filament compression on all that length contribute to stabilize the pressure inside the nozzle? I like printing fast, and you know it. But the length of the tube required for my printer size made the retraction and pressure advance to slow things down by
way too much.
So slow that I could not live with this. What could I do to smoothen the extruder system without using this long tube? So let's break the extruder system into elements so we can properly pinpoint to the right root cause. It all starts with the stepper driver, providing inputs to the stepper motor. With the help of its pinion gear, the stepper motor will then drive the extruder plastic gear that is connected to the shaft, holding the extruder gear itself. That extruder gear is then providing power to the idler gear via the gear teeth at the end. Both gears are then squeezing the filament and pushing it downwards into the hot end. This sounds like a very simple system, but I think we can shorten that list even more. So just remember, for my Bowden print that looked so good before, I was using the same filament, the same hot end, the same stepper driver, and the same motor. So let's remove them from the equation for now. With a methodical approach, I printed the same G-code while changing only one parameter at a time. This allowed me to eliminate many things that had no significant impact on the surface quality. It was not due to microstepping, not due to motor current, not due to the motor itself, not to backlash between the motor pinion and the drive gear, not the meshing of the idler gear. Yeah, you probably think that this has to do something, but trust me, I even went and grinded the teeth off of one of my idler gear to test that one. No impact. I then swapped to another extruder gear assembly, one that came into a BMG clone that I had in stock. Surprise! The results were much better. I still had a bit of that artifact, but overall, the texture was way smoother. We are getting closer, I feel. Looking at the BMG gear carefully, I realized that the hobb gear could get out of axis. The thing is that the current design allows for the manufacturing tolerances to affect the position of the hobb gear on its shaft. If tolerances for the gear inside diameter are at the maximum, and the ones for the shaft at the minimum, the set screw will be able to pull the hobb gear out of its rotation center. The gear will now be rotating in a manner where we get more plastic on half of the rotation and less on the other half of the rotation. We could picture the flow variation as a sine wave. You can try printing a 30mm single-wall cylinder like this one, and then change the timing of this sine wave by increasing the extrusion flow or reducing it as you are printing. See how the artifact pattern is completely changing with flow variation on this tube. To quantify the flow variation, I measured the amount of runout of the hobb gear of my BMG units and noticed a slight amount of deviation. But how much is too much? Can a runout of 3/1000 of an inch create such an artifact? Yeah, okay, I know, inches. Here in Canada, we mix both systems. I drive at 100 kilometers an hour, but I am 6'1" tall. Anyways, because 3D printing is using the good system, let's convert that 3/1000 of an inch into something more meaningful. 3/1000 of an inch multiplied by 25.4 millimeter per inch gives us 76.2 microns. That still does not sound like a whole lot to me. But what does that really mean when we print? Let's run a little simulation. Our gear has a diameter at the hobb of 7.2 millimeter. If we offset that gear by half of that total runout that we measured before, we are going to shift it to one side by 38.1 microns. The gear assembly will now act as a 7.276 millimeter hobb gear when that side reaches the filament. Then when the opposite side gets to the filament, the effective diameter of our extruder becomes 7.124 millimeter. So a total oscillation of 152 microns. Now we can start to feel the impact of this situation. In theory, if our gear was perfectly centered, for every millimeter of extruded filament, we would get 2.405 cubic millimeter of plastic. But because our gear is tricking us, We will sometimes get more plastic, and other times we will get less. When the hub gear is shifted towards the filament, the hub gear will pretend to have a diameter of 7.276 millimeter, therefore being 1.05% bigger than the perfect 7.2 we had earlier. And because of that augmentation, we are not getting the requested 2.405 cubic millimeter of plastic anymore. We are getting 2.43 cubic millimeter. On the other hand, we are only getting 2.38 cubic millimeter of plastic when the hub gear is shifted at the opposite side of the filament, and therefore pretending to be only 98.94% of the real thing. Between the two scenarios, we now have a total difference of 0.05 cubic millimeter of plastic, and this is for only a length of 1 millimeter of filament extruded. Okay, I give it to you, we are back with small numbers again. But bear with me for a moment. If we were to take that theoretical 2.405 cubic millimeter of plastic from our perfect gear and shape it into a 0.5 millimeter wide by 0.1 millimeter thick layer profile, it would have to be 48.1 millimeter long. Where am I going with this? Remember your mom's cake icing bag? Or that silicone caulking gun you used the last time redoing the shower seal? What would happen if you apply that icing or caulking at constant speed while maintaining a nice and even layer thickness, but you keep varying the flow? You guessed right, you're not going to push yourself into going faster, and neither will you go higher. Only that nice extrusion bead is now going to be wider. I prepared that little 3D model to show the difference between the lean layers and the over-extruded ones from our previous example. The under-extruded lines have now a width of 495 microns. The over-extruded ones, on the other hand, have expanded to 505 microns. Although this is only a variation of 10 microns, we can clearly see on this model the impact on the surface quality. This is an eye-opener for me. The extruder should be considered as a precision instrument. We need better components for our direct drive race machines. The level of precision on the quantity of material extruded is also directly impacted by the manufacturing tolerances of your filament. If we use the same simulation model, a variation of plus or minus 0.05 millimeter on the filament diameter could mean a layer width varying between 0.47 millimeter wide and 0.53 millimeter. This is huge, but usually this variation will be spread over a greater distance of filament. But this is something to keep in mind. Look at this weird spiral caused by the poor quality from the end of a spool that I had in stock. If you wish to up your print quality game, it is therefore important that you choose a filament manufacturer with pretty tight tolerances. The work involved in making this video started back in August. A lot of work, material, components, and time has been invested. My patrons were able to read a weekly report on my findings during this journey. Dear patrons, thank you very much. You are covering a portion of the costs involved at producing these kinds of research. If you too would like to help me out and would like to benefit from the detailed insights about my experiments, I invite you to visit my Patreon page by clicking on the address link here below in the video description. Over and above the support from my patrons, I also benefit from a huge moral support from my good friend Vez3D. Well, perhaps he is not the best to provide any kind of moral advice with his lack of self-discipline, but I do appreciate our long scientific discussions and his large sense of drama. I like what Simon does with his VZBot. Nah, seriously man, thank you very much for allowing me to bounce ideas on you and for keeping me focused when I get discouraged. Thank you, brother. Understanding the considerable variation that such a radial runout would give, I approached Bondtech and explained the situation earlier this year. They've been super responsive from the start, and we then worked on a revised gear assembly that would combine the shaft and the hub gear as one single part, therefore removing chances of having a hub gear out of center. After a few months of wait, I was very excited to try these new gears on. If this works, we will be able to maintain our tiny direct drives extruders and get much better quality. With a little over 5/10 of a thou, inches again. 12.7 microns, should I say, of runout, these shafts should be much better. Well, nothing in life is easy. I am getting the same artifact, once again. A little less pronounced, but it is definitely still there. Just like a ton of brick in the forehead, it hit me. What about the plastic gear? Oh my God. It was such a downer to realize that I was focusing on the metal gear, while the plastic gear was just as bad, if not much worse. In some cases, reaching up to 152.4 microns of runout. So I had to try pressing on my best plastic gear coming from the BMG clone unit that I had onto that new shaft from Bondtech.
Fuck.
Some days are better than others. That was not the case for today. I will sleep on it. While in bed, I started to shop around for better drive gears. Could we get some machine gears pressed on? Should I completely change my extruder design? Just as I was ready to close my eyes, this thing appeared. Filament just released a new improved gear. Better precision, apparently. Seems to be a machined plastic gear. Oh well, let's order a few. 4 weeks have passed and here we are. The new gears have arrived. How precise are they? Well, they are not perfect, but with just under 50 microns of runout, this is by far the best units I've seen. Let's try to press it on the shaft, but this time around, I will preheat the shaft before trying to press it in. There it is. It looks very good. And I was able to maintain the initial runout tolerances intact for both the plastic gear and the hobb gear. And now let's print. So right now I could teach you a few swear words in French Canadian. Because let me tell you, I've used a lot of them. So new shaft more precise, new gear more precise. Looks a bit better, but it is not what I'm expecting. There is definitely something else going on there. What is that artifact? Once again, changing flow of the extruder would change the pattern. It is definitely related to the extruder. Could it be the idler hob? At this point, even if I don't have any logical theory about it, let's try to swap it and replace the idler hob gear for a stack of plain bearings. I may get less traction, but at this point, I could not care less. Oh wow, it is gone. But why? What is going on? Why is that artifact gone? So the idler gear seems to hold the answers to our questions. So here's my theory. If the idler gear shaft is slightly tilted, and it wouldn't take much, as we've seen earlier with very small numbers having noticeable impact on the surface quality, this tilt could apply a force at angle on the filament. This means that the filament could be pushed forward or backward and therefore changing its position inside the hob gear groove. Changing position in the groove would also mean changing the effective extruding diameter of the hob gear. Using our CAD simulation model, we can see how much impact can this condition where the filament is walking in the groove have on the print surface. It can definitely throw things off by a much greater margin than our 76 micron hob gear runout had. Look at that. Incredible. The design of my tiny extruder could be in cause for not maintaining the idler shaft parallel properly to the drive gear. The limited amount of axial backlash on the idler might not allow for a perfect self-alignment of that hob groove. Print accuracy of the extruder body could also play a role. Many factors need to be perfectly under control for an extruder gear system like the BMG to work properly. Now that I know the source of this annoying artifact, I can retest properly the hob gear shaft assemblies I have in stock using an idler made from bearings. The first one on the left was done with the Bondtech original extruder gear shaft assembly. We can clearly observe the ripple artifact from the extruder gear wobbling around its axis. In the middle comes the new shaft assembly that I made from the Bondtech new experimental integrated shaft and the plastic gear from Filament. The repetitive rippling is practically gone. Although a few artifacts are still showing up, the quality is much better. And on the right, I reprinted a tube using my Hemera in Bowden mode to compare. Although it is still the best tube from the three, I think the results obtained with my revised direct drive configuration is pretty close to what Bowden gives. We have to remember that this observation is being done with the light coming from the top, and every little variation in flow will show up, either caused by PID heater pulses, filament homogeneity, filament diameter. Nevertheless, it is clear to me that the more precise your extruder system will be, the better surface quality you'll get. I'm currently having discussions with Bondtech for a potential solution to be offered that would help those of us with a compact direct drive extruder based on the BMG internals. I'll keep you guys posted when something is ready. In summary, the last 2 months have taught me a lot in what is going on into the extruders. They are probably the most important part of a 3D printer. Their impact is also amplified if you're using them into a direct drive extruder, because we're not benefiting from the dampening effect of a Bowden tube. Every single little defect or variation will directly be translated to your print. And as explained today, it does not take much to create visual artifacts. I hope this video can help you to increase your print quality. Let me know in the comment section below what was the mod that had the best impact on your print quality. Now that you have seen me naked with all my defects, let's get dressed. Let's put back on this very nice light dress that makes us shine under our best angle for the photo. See you soon. Happy printing.